So my job for a long time has been making stuff, inventing, building, designing. And I kind of lamented all of my amazing academic friends who do incredible work, particle physics. I know like double doctors and people like that. And I get papers from them. They email me papers and I'm like, look at what I'm working on. And I'm like, that's really cool. It makes me wish I could sit in front of a test tube. I can't. But I get to take what they're doing and do interesting things with it. So neurobiology has actually become a big part of my work in doing human interface studies and doing like vision studies and how do people perceive color and how do you make illusions and things and how do you make products that ask to be used that actually their function is inside of their design. And I recently got this whole big pile of papers from, if I remember his right name, Dr. Richard Wolfman, which is a good name. And they were all by a collection of scientists working on how perception of 2D art is actually wacky and odd and awesome, and how artists for a long time have been finding these shortcuts into human perception by making, a line drawing doesn't look like a face. It looks like a face to you, but it doesn't look that much like a face. It's just two eyes and a thing and a mouth, and you're like, oh, it's a face. It's because we have this really sophisticated software going on in the brain that's analyzing images fast and frugal. And I'm going to be talking about that, and it's called Art is Wrong. So, next one. At some point I'm going to have to walk with the mic to actually point at stuff. There. Is there enough mic cord to do that? Machines. In the extreme future, microphones will be portable. So here you have the underside of a brain. Your brain, perhaps. So it's generally divided into a couple of different lobes. The whole time I'm going to be talking as if pieces of vision and pieces of thought go on in specific areas. This is a convenient way to think about things. I'm going to get into some examples of why that might not be true. That individual things happen in individual areas. But for the most part, I'm going to be talking about how data arranges itself through the brain. And it's because it's lobed off. It's got different sections that communicate with themselves more than they communicate with the outside world. So up here you've got the frontal lobe. A lot of people are interested in that one. It's boring. The middle lobe, the temporal lobe, a lot of people like that one. Boring. The occipital lobe is what I'm going to be talking about because it has all of these interesting, super sophisticated vision processing things to it. And if you go to the next slide, it's right back here. It's the butt of your brain. And vision actually comes all the way from your eyes. Next slide. All the way from your eyes into the occipital lobe. So everything goes eyes, back of your brain, other stuff. And I'll be explaining why that's weird and cool in a bit. But a lot of my stuff is going to be from a couple of different professors, Robert Cavenet and Peter Vishton. But academics, cool people. Next one. So here's long piece of cord, long bundle of nerves that go all the way back to the occipital. So the eye passes all of its data all the way back through your head before it actually meets the brain, which is it's an interesting way of arranging stuff, and that's because our brains were a lot smaller millions and millions of years ago. That you're a little tiny crawling mammal, and your brain is a lot smaller, less of the more sophisticated stuff that's going on. Vision still a very important part of being a mammal. So as our brains grew, the nerve had to get longer and longer. But a lot of this analysis and a lot of this analytical software stuff is still exactly what it's been. Well, not exactly, but it's still very much like what it is in other mammals. We've got this way deep down primitive processing stuff that we share with many other creatures. Next slide. And the kind of cool thing about this whole system is it's lossy. So your brain is doing stuff fast and frugal. Your brain is looking at the world and going, that's not a bear, and that's not a bear, but that could be a bear. And I could sit and think about that for a while. And that would probably be a mistake. You have to do this kind of processing really fast and really efficiently, or else you get eaten by what might be a bear. That these kinds of things are immediate. And so we have all these failures, we have all these problems because we're looking through the world and we're like, face, that one's angry. And it has to happen fast, and you start making mistakes because your eyes are taking in all of this data and they're chunking it down into useful bits, and then the data starts getting scrambly, and that's why two-dimensional art works. So your eye is composed generally like this, where light comes in the scientifically called the front bit, and the back bit, this is known as the eye butt right here. So in the back end, so our eyes work a little bit like a film camera, in that you have all this light coming through, and then it comes to the back, hits the back of the retina where there are all these light-sensitive nerves that are photodetectors, essentially. You have photodetectors for different levels of light. You have photodetectors that are looking for specific colors that are sensitive to certain colors or certain frequencies of light. I'm sure you saw like diagrams in high school, rods and cones, that the portion of the back of your eye that's sensitive to the most color and to the most detail is actually this little tiny area. So you have this little bit thing called the fovea, which has this 20-degree cone of vision in the middle of your eyes where all the details get seen and all the colors get seen. If you look at an eye and you look where it's sensitive to color, the outside of that region, the outside, the non-foveal neurons in there, aren't seeing color. But you don't look to the side and go, ah, there's black and white in the side of my vision. That person's wearing pink shirt, gray shirt. You don't notice that your vision transforms even though I look away from a colored image and I no longer see color. So the problem is your vision, your impression of your vision persists. You have this like heavy idea that your vision is really complete, but it's not. And I'd like everybody to do a test with me. So put your hands out in front of your face. I'll do this. So put your hands out in front of your face and fix your eye. Like close your left eye, fix your right eye on your left fingernail, and move your right fingernail without moving your eye. There should be a place about 4 to 5 inches away from your left fingernail where your fingernail on your right hand disappears. So it's eerie, because you don't see a black spot in your vision. You see a just ignore that. You have a just ignore that field in your eye. And so the problem is there's actually a nerve that comes into the back of the eye. You know the long nerve I was talking about? It's a couple of million neurons all having they have these dendritic ends and these axial ends, and the axle end flows all the information back. There's all this information that gets bundled and thrown back to the back of the brain. And so you bundle all of these together, but the eye can't really be that deep because it has to twist and it has to do a lot of mechanical stuff. So if you extend this back to make sure that this still is stuffed with neurons, you have a very differently shaped eye, and you have evolution didn't select that way. And it's okay because you don't notice that this bundle has no visual receptors on it. So that blank spot that you saw in your vision is a complete lack of vision right there. And you don't notice it. Your eyes just fill it in. Next slide, please. Here's another illustration of that. Everything kind of comes down to the center, and then blood flow goes also through the optic nerve. Next one. So this is just kind of a diagram of foveal vision, and right outside of foveal vision you have a blind spot. It's about the same on everybody, where it's about 30 degrees left of center, or right of center, depending on the eye. Next one. We already did that. So stare at one of these dots, and don't stop looking. What you will notice is that the other dots disappear. If you stare, it's probably loaded, which I love. Internet. Thank you for spoiling my presentation, Internet. That's okay. Yeah. Oh well. So maybe it'll work if you just stare at one of these dots. Stare at it, stare at it, stare at it, stare at it. What will happen is the other dots will drift into the background. You'll be unable to see them unless you change your focus. So your eye is always moving around. It moves around in saccades, these little jumps of motion. Your eye almost never does what's called smooth tracking. Almost all of your vision is blip, 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 blip. And when you move your eye, you're actually catching stuff in your fovea. You're actually scanning the scene. So you're waving that kind of flashlight of vision all around. The weird thing is, when you're not focusing on something, it's mostly persistence of memory that causes you to put the scene together and say, it's whatever was there was there. If you have a moving background, details that might be stationary get overwritten by the idea of motion, by the sensation of motion. that the moving background overwrites that data. The moving becomes more important than the dots. If we go to the next one. Oh, here's Albert Einstein. Hit right. Albert Einstein. Hit right. Marilyn Monroe. So one of the interesting things about the way that your eyes process vision is that you have different neurons that are actually sending signals in different spots in the occipital lobe that are sensitive to certain kinds of data processing. So some are looking at detail. Some are really, next slide. Some are really, really hyper-focused on detail. So you can see all this detail stuff. Next one. Next one. Oh no, it's Voldemort! That you're looking at these detailed images, you're looking at these little bits of detail, and they become important if they take up a certain portion of your vision. If you're looking at details and they're close enough and they're dense enough, then you start seeing an image that can flip when other processors take over. So there are some processors that, if there's not enough detail in the scene, will start doing things like face recognition using different software. So something can be two faces. Here's the eeriest one. All right. So, George Weasley. Oh no, it's the other Weasley twin! Okay, the next one. All right, so you're experts, you're face experts. You are, yeah. So you're face experts in the sense, ouch. Because he looks nice this way. So you have these areas in your brain that do complex visual processing. A lot of that happens in the amygdala. Now saying a lot of that happens in the amygdala is that the amygdala is very, very active when you're looking at faces. It doesn't necessarily mean that the amygdala controls all face vision. That's like me, I have a blender, I make smoothies, and I make walnuts in the blender. I put the blender in an fMRI, which is a bad idea, but you put the blender in an fMRI which measures electronic pulses around places, and since blood is made of water and water is magnetic, there are all these things you can do to measure the rate of blood flow and the amount of around electrical activity that's happening that it makes an electric distortion inside of the fMRI, and you can read it. So you can read where the brain needs blood, and you're like, amygdala, you need blood, you must be in control of faces. But in the blender example, I make smoothies, and the blender does this thing, and the motor goes, and I measure it, and I'm like, the motor goes when I make smoothies. And I chop walnuts, which you shouldn't do, but from experience I have done. And you chop walnuts, and the blender works even harder, and you say, aha, I have made a science. I discovered that the motor is the walnut chopping part of the blender. And that's not really true. So you do another science, and you drop the blender, and it will still do smoothies, but now the motor's a little broken, and it won't do walnuts anymore, and you're like, aha, science number 2. I have discovered, through 2 pieces of evidence, that the motor is exactly the walnut chopping part of the blender, because now that the motor doesn't work as well, it doesn't do walnuts. So I'm talking about these things, they're a good way of talking about different structures for processing in the brain. They're not 100% necessarily true. It's just a good way of talking about it, and it's pretty likely, but not guaranteed. So you're face experts. So your amygdala lights up when you see faces, but it doesn't really do that when you see upside down faces. So this guy doesn't look, that's weird, but it's not awful. Next slide, please. That's so much worse. This is called the Thatcher illusion because the first person this was done to was Margaret Thatcher. So what goes on is the amygdala lights up when you see faces, and you're kind of a face expert. You're really biased to see faces, and you pick faces out of clouds, and I'm gonna go into parapodia in a little bit. But what's kind of weird is it's like being a wine expert. And an upside down face is not filling in your wine expertise. It's a glass of water. But this is like a 2010 Vinny Vito served over crushed ice. This is a terrible wine. And so the thing with your facial processing stuff is if you become an expert at something else visually, say you're great at identifying birds or identifying cars, the other thing that will happen is you'll show someone upside down pictures of birds and cars, and their amygdala doesn't care. And then you show them right side up ones, and suddenly the amygdala is doing the same kind of processing where you're using the face recognition centers of the brain, you're using that software to do things you're an expert at, which is kind of cool. So you can actually train people in imaginary objects, give them imaginary pictures, and so a naive viewer, a person who's never seen a picture like this before, you give them families of objects or families of people. You have these, drawings that are like, hey, here's a Hingle Smith. It's an imaginary object, and you start putting them into families. The experts in Hingles will start having their brains concisely distribute data in their head, where they'll start out looking at Hingles with lots and lots of processing, lots of new information, and eventually they'll become experts at Hingles, and they'll only use their amygdala. Next one. So let's get on to art. And just tell me when I have 10 minutes, and tell me when I have 5 minutes.
You're good on time.
Oh, good. So here is a portrait of, I think it's St. Francis as Brother Wind. And these are two different kinds of image sorting analysis software being applied. So one of these is looking at details. One of these pictures is all of the contrasting lines in the piece. This is just a piece of image software that's looking to create contours out of a photo. That's fairly meaningless. That's just some fairly meaningless blobs, but that's the contrast that's in the piece. That if you scan this with your eye, a lot of this same data will be being observed by your retina. But this makes a lot more sense. This looks so much more like that. Why the heck is that? Like, why is it that these two things are slightly different ways of doing image analysis? This one means a lot more to us. It says a lot more about that scene. We recognize that as a piece as a figure. That is a blob. Next one. Part of this, I love this project. Part of this is because we're really, really hypersensitive to outlines. So a lot of your vision isn't actually binocular. So you'd figure, you see with 2 eyes. You're telling 3D stuff with binocular vision. I know that, that guy is in front of that guy because 3D, the space. Not true. Much of our processing is actually going on a 2D image. That we're not really using that, your binocular vision is relevant for things that are about arm's length away. You're not seeing with mountains with binocular vision using the skew between I1 and I2 to be like, that mountain is exactly 300 feet away. You're not doing this. You're actually using all of this 2D processing to do things like, this is in front of that, this is occluded by that, this is why this is the horizon. And you can trick it in weird ways. People are so sensitive to this, and especially children, you can kind of tell that they draw in outlines because we're really sensitive to outlines. Next one. Here's a Dali. So this is Abraham Lincoln. We're also fairly sensitive to blurriness. Next one. So here is a piece of an image analysis software that's looking through to find blobs of color. So what it's doing is it's taking a whole look at the image, and then it's kind of having competition between a bunch of randomly selected points. So you select points, and you have them blur out. You have a point, and it populates as a big blur until it meets another point that's going to try and define a line, and the hardest, strongest lines will win. This is kind of happening, next image, so it's an image of that. It's all the relevant contours of that. So this is happening inside of your eyes and inside of the neural processing that's going on in the occipital lobe, is that you have all this competition between neurons to be king neuron, king of the signal. So what happens is that you have a bunch of neurons. They're all getting signals at the same time. They're all getting this buzzing wash of information, and it's pretty meaningless. And some neurons start being like, you off, you off. They do this thing called directional inhibition, where they will start turning off nearby neighbors that are not signaling as strongly as they are. And they'll be like king neuron. They will eliminate contrary signals. They will eliminate cascading signals that don't fit their model as well. And the weird thing is, over time, that combines with another feature called long-term potentiation, where neurons will remember the last signal they liked. So you have this wave of excitation. You have signal, 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 signal. Neuron's like, fuck it. Neuron doesn't care. Signal, signal, signal. Finally, you get a certain signal of a certain variety. The neuron goes wild. It calls all of its friends. And the weird thing is, if it gets a similar signal of a much weaker threshold, it'll pop off again. And so this lasts for a long time. This is called long-term potentiation. So you can kind of picture, if you have a wide cascading variety of signals, over time it starts making some sense. The next time similar signaling comes in, it makes greater sense next time. The structures are already habituated to give the same kind of signals, the same kind of sense. Next one. So we're actually really sensitive to a couple of things about 2D images. This seems to be a transparent circle. So there's a transparent circle laid on top of a black and white, a black card, white card. This does not read as that at all. This reads as two halves of circles or two painted objects. It does not read as a transparent circle. And that's just because of the way the lines cross. We're actually pretty sensitive to that in establishing what's in front of what. That the way we do depth is a lot of what's in front of what, what's occluding what. How are my outlines that I'm establishing, that I'm seeing, occluded by other things? And so this is starting to, you can kind of start to see how this happens in paintings. Next one, please. So everyone, most mammals recognize paintings. Most mammals recognize 2D images. Most mammals recognize photographs. You can actually get monkeys to recognize photographs, and you can show them angry monkeys. And they're like, ah! But they'll also, they were fooled the first time, but they also adapt, that they're not 100% taken in. Over time, they'll be like, oh, it's a photograph. For some reason, even they will start understanding this seems to be a face, but it's not a face. It's a photograph of a face. It's different, which is weird. Next one. So we've been doing paintings, we've been doing images for a long, long time. This is a 15,000-year-old image. This is from Lascaux Cave. Next. This one is from 700 years ago. This is from Janjan Ping, I think. But the drawings are remarkably similar. The space it depicts is remarkably similar. They're both a horse. They both are made in outlines. We've been doing this. This is not a cultural convention. It's not just a habit that we draw in line drawings. It's something fundamental about our brains. Everyone sees and understands line drawings unless there's something screwed up about your brain. And this happens to people. Occipital lobe damage will have people unable to identify things. You're very familiar with being able to identify where in an image, like there's a person over there and a person over there. You can point to stuff. But you're also very familiar with not knowing what something is. You see a new thing. I have this happen to me all the time on the highway. There's something on the side of the highway, and I'm like, dead body, roadkill, plastic bag. And you look at, oh, it's a plastic bag. Uninteresting. But it captures your attention for a little bit because it's a new brand of thing. It's a new, what the hell is that? You're very familiar with what the hell is that, but you're not very familiar with not knowing where. But there are kinds of damage that can happen to your brain. And there's a kind of a lower tract of neurons. There's a set of structures that bridge some of the underside of the brain, some of the visual processing areas that can get damaged. And so people will be able to tell you exactly what a thing is. They'll be able to focus their eyes on it. And they will not be able to tell you where the hell it is. There's a visual disorder where people will not be able to tell you where something is, but they can read its label. It's really eerie. So next one. So our brain has to do all this signal chunking because we have limited bandwidth. We have a limited processing power. Stuff has to move through, and we have to throw out old data and move in new data really quick. And so that's why you see all of these visual errors. That's why you see all of these problems and all these tricks come in it. Next one, please. This is a painting from Salvador Dali. This actually touches on a little bit of, there was these psychologists called the Gestalt psychologists who found out that you could actually change what people saw by giving them new data about the scene, that your perceptions. So you can kind of see this as figures, 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 lady. Or you could see it as figures, 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 a bust of Voltaire, lady. You see the eyes, the nose, and the mouth. And once you see that, you should be consciously able to flip back and forth between them. That you should be able to look at the faces and see ladies, and then scan the image again and see Voltaire, and willingly back and forth snap between them. Which is, you seem to be able, you're not telling yourself there's Voltaire there, you see it. That your conscious frame of mind actually has a cascading effect on the observed image, where that realization comes to you without effort. It's not a mental exercise. You give yourself clues, and the image appears. Next. So our habit of making images in clouds, of seeing animals, places, this kind of animism that we've got, where we see faces in everything. And I'm going to probably make a mangling of this, perioidea. Next. We see images, faces, everywhere. And it's because the signal processing that we do is obsessed with finding faces. We're so concerned with finding faces and things because it's very important. It's very important to know how the other monkeys around you are feeling. It affects how much food you get. It affects how long you live. It affects lots of things about your life. And so we're very concerned with picking those out of images, and that goes wrong a lot. Next. We're actually so good at this, we see it in things that don't look anything like faces. Next. So you see a crowd here. You see a crowd of people here. You're doing the same analysis that you do on a three-dimensional image. You see a crowd. You probably see that guy right there. Next. He's not really made of much. That's not much like a dude. That's just a blob. And the reason is you're so sensitive to this stuff, you're picking things out of blobs, and that's what artists are taking advantage of. They've been doing neuroscience a long time before neuroscientists were doing neuroscience. If you figure out the way you can depict things as looking real, you get to figure out what you can leave out of vision. And what vision is doing, why those emissions don't make any difference to the image. If you can leave some basic physics, some basic architecture and lighting and visual stuff, if you can leave human beings out of an image and just have a blob and still have us recognize it, it tells you something important about what we're doing with our eyes to recognize people. Next, please. Yeah, the mind's eye is a weird term. It's weird to think that you're consciously analyzing the world with your eyes, because so much of this is coming to you without any analysis, so many faces, so many identifications. When you know someone's a family member, or when you know that's a person you haven't seen in a long time, it comes to you without effort almost every time. Next. This is either fighting monkeys, or it's Darwin. This is another Gestalt psychology thing where you can flip back and forth just by changing what you're looking at the time. It's an interesting, eerie illusion that if you focus on the details, you'll start being able to see the line drawing. If you focus on the whole of it, if you scan it generally with your eyes, you'll be able to see Darwin again. It's actually two fighting sets of signal processing that are going on. There are two fighting areas that are trying to give you the signal, and they're trying to inhibit each other. They're trying to turn each other off to be king neuron. And sometimes they flip back and forth where no one will be king for very long. Next, please. So I'm going to talk, hopefully the YouTube thing loads. I have no guarantees, the internet has been a little spotty. So this is only 2 positive frames and 2 negative frames. There's only 2 frames of motion in here, so just the same 2 frames, also negative. If it loads, it loads. If it doesn't, it doesn't. It's an interesting effect. So, you see motion here. You can kind of see the roads continuing around, the trees are going around, but it's only the 2 frames. It's a very, very limited spectrum of motion. We infer motion on it. It's because we're not doing motion processing constantly through the image. We're doing motion processing in little chunks. We're using significant signals about what happened before and what happened after to turn 2D images, individual 2D images. That's kind of what's happening in your eyes. You're taking these frames, 2D images, and you're turning them into motion. And there's actually some evidence, next one, that depicting motion in motion lines and in multiple figures in a scene actually represents what's happening in a part of our visual processing. There's some decent evidence that motion lines actually change our eyesight to show us that we're actually seeing a moving image. So that the same reaction to motion lines is the same reaction to moving images. It's slightly eerie that a still image can contain motion information that you can't help but see. Next one. All right, if this loads, this loads. This is a Figureground Illusion. So you see a triangle. There's no real work going on to show you that there's a triangle. That's because we have this habit of trying to simplify the scene. There's something about vision that seems to make you simplify it. Many people will see this other triangle that's popping in as being slightly darker in color. You'll be able to see that this is a little bit darker. Most people see that there's a slightly grayer triangle underneath, but it's not there. There's no color change. What happens, part of your visual processing is isolating bodies and saying, this is different from that, this is on a different plane, this is on a different level than that, they must have a different shade. It even works in 3D. You still see the little chevron there. And if the movie's fully loaded, you should be able to, it still works. with the other one. Next, please. So this is something eerie that goes on in a lot of our art. This is from an artist. I will, I think it's Robert Connors. I'll get his name for you. I'll upload this lecture and the papers that I've used in my notes to my server and then link it on the XFF website, or I'll link it on the XFF Facebook, and you can have it. You can download it and share it all you please. But if you go to the next slide, this artist actually uses canvases that are bent. Canvases that are bent in an interesting way, and maybe you will detect the illusion. Patrick Hughes. Patrick Hughes is the artist. Oh, YouTube. I'll use my mind powers on it. What? What just happened? Oh. It's not my laptop. It doesn't seem to be the laptop. Oh. No, the projector is just off. Because otherwise there would be a little warning thingy. Technology. Oh. Yeah. Okay.
Great lecture, though.
Thank you. If it boots back up, I'll continue where I left off. If it looks like it's dying, I can do the rest of the thing without slides. It just won't be as pretty.
You're pretty.
Aw. Thank you, Dollface.
Your outfit.
So while that goes on, I'm going to tell you an interesting story about brains eating themselves. So there's a professor named Ramachandran who does some amazing breakthrough works on phantom limbs. So you lose a limb, which is a terrible thing to happen. Admiral Nelson actually, if you know Admiral Nelson, the naval guy, British Navy guy, got his arm blown off by a cannonball. And for the rest of his life, he would write in his journal, the pain that was with me when the cannonball took my arm off is still with me today, including the fact that I can feel my hand, my missing hand, clutching in a fist so hard I can feel my fingernails break my skin. That in his missing hand, he felt a pain so great that he felt his fingernails were cutting his hand open. In modern research into people who have lost limbs, we can actually track you can poke somebody on the body and have them in fMRI and track where those signals are going through their brain. There's actually a reflection of all of your nerves, all of your sensory nerves, on the inside of your brain. There's an internal homunculus. So what happens is all of the nerves that are responsible for hot and cold and itchy and pain are also making signals on the inside of your brain. And you can scan someone's brain with phantom limb pain, and you'll see that those signals are persisting. You can see that they're still getting the same pain signals up in their brain. And so one of the hard things to, I'll finish this quick. One of the hard things to observe is no worries. Let's see if that can be managed recently. So one of the weird things is if that signaling keeps going on, what will happen is that thing will persist. You remember I was talking about long-term potentiation, where that signaling still happens and still preserves that little area, that little nub, and not everybody has phantom limbs. If you take a person, say, who has phantom limb cramping, say they feel that their arm is twisted up in a very strange position and it really hurts and they're getting a cramp in their phantom limb, you can actually put them in a mirror box and show them their whole limb as their phantom limb. And what will happen is they can flex their phantom limb and they will feel their phantom limb flex. And they will be able to stretch it and feel the pain go away. And over time, you will observe that that area of the brain that was responsible for the nerves of the phantom limb gets eaten by nearby signaling areas. That other areas of the brain are doing this king neuron thing. They're doing this signaling. You'll watch this wave happen and you'll poke somebody on the limb. They'll be like, no feeling, no, not there, there. And so you can do touch tests. So arm and hand and face are really close to each other in this map of the brain. They're very near to each other locationally on the map. And so what you can do is you can poke somebody on the face, and they'll say, you're touching my face, you're touching my face, you're touching my face. Doctor, you won't believe it, you're touching my hand. So what happens is the nearby cross-writing, the nearby activity of the brain rewriting itself, competing for signal, made it eat everything in between arm and face, but fingers are still there. All right, let's see, that's fine. So I don't think the YouTube will load. Do you trust it?
We tried.
Sure. So, see how long it takes for the illusion of this to... Damn it. Not going to happen. So the trick is, you bend around and it looks like the buildings are moving and it looks like you're actually in the scene until you realize that it's just the canvas bent forward at you. The canvas is painted like this. And so it's an eerie illusion because it makes sense for a while, and then there's this eerie flip that happens, just like the Voltaire face flip, just like the face flip that happened in the Dali painting. You have this flip, and now the image is different. Now you make sense of it in 3D. The illusion of the illustration kept you captivated for long enough that you read it in this eerily 3D way. All right, so shadows. I'm going to briefly talk about shadows and the construction of images. So shadows have been around off and on. This is a couple thousand years old Greek painting. Next one. This is a slightly more modern Greek mural. So you can see the use of shadows. You can see that he's casting a little bit of shadow on the horse. Next one. In Eastern art, it seems that the history of art has been more indifferent to shadows. You do or do not need to have them to be able to read the scene. Everybody makes sense here. I mean, they're floating in a magical space, but they're probably supposed to be floating in a magical space. This was probably done intentionally. They don't really need shadows to have them be present in the image, which is really weird, because you never see a scene in real life that doesn't have some kind of shadow. It's very, very rare that you can see stuff and there aren't shadows. Next one. And so that's why something like this seems to make a lot of sense, even though it's freaking wrong. So, in this image, tell me where the light source is. Because there's light source coming from here. There's a light source, those shadows coming from back there. There's also a light source coming from over here. There's also a light source coming from right over there. These ladies have super dark shadows. These people in here, in this nice, evenly lit space, even with the wall being nice, bright, should be reflecting light on them, they have super heavy shadows. These don't work in perspective. If you zoom in, a lot of these shadows are wrong. A lot of these shadows don't line up with each other. A lot of them are going in different directions. They have shadows that go over here. The columns have shadows that go up there. These people have shadows that go in a slightly different direction, and they're all really dark. Yep. That doesn't seem to matter, does it? That this reads perfectly fine without the presence of a lot of essential things that happen in everyday life, that you see constantly. It seems to be that we don't care terribly much, that it's not necessary to understand an image. So on the inside of our heads, the reflection of the image is shadows, whatever. So next one. So Patrick Cavanet talks about this a lot in his work, that we seem to have an internal physics, a physics that makes sense to us, that is part of the way we see the world, the way we read an image, the way we read everyday life, that doesn't have anything to do with everyday life. What it has to do is the important stuff to us, what's fast, what's frugal, what we can get done, what we can shove into our eyes and do signal processing on so we can move on to the next image. You might remember that I was talking about the saccade. I was talking about saccades. I was talking about how the eye darts back and forth in between stuff. It does it fast. You do more saccades daily than you have heartbeats. But it does it slower than it does it slightly at the same time than your refresh rate on your eye. That what should happen, visually, if you look at the amount of time it takes to refresh the chemicals in your eye, what should happen is you see a smear as you turn your eye between saccade. You should see a smear that happens between here and there. There should be this blurry patch in your vision. What happens is in between saccades, as you're focusing on different things, your eye shuts off for a second. So there are times when we can make sense of the world through a painting. It's not that paintings are all lies. If you zoom in on this, next one. We know shadows don't do that. It's immediate. It's immediate that shadows don't work this way. This is just a present thing that we know about paintings. We know that this isn't a guy stabbing the devil. Like, we know implicitly that this painting isn't a real depiction, that it isn't a real image, that we're not looking into a magical window. We're seeing a depiction. We see this fictitious universe. And there are these laws that we understand about this fictitious universe, and one of them is that shadows should never do that. It's just immediate, which I find incredibly strange, that there can be all of these things wrong with the image. There can be all of these things where, skin doesn't really look like that. This is a painting of skin. This is made of paint. This is two-dimensional. All of these things should be, yes, this doesn't work as an illusion. But they do. Next. This is actually a painting that makes fun of the painting of perspective. So you might see a whole bunch of things. You can read this image, like this image reads in 3D, despite the fact that this guy's fishing line goes behind that guy's, that this person on the hill over there is talking with the lady out of the window, that this guy's shooting a duck on the opposite side of a bridge, that this sign is behind the trees, that these two barrels are completely warped in perspective, and that you have here, you have a set of cows where the largest one is in the distance and the smallest one is in the foreground. Yet, this image scans. You have a sense of the space in this image. You're able to see these in little, discrete packets. And so what we do is we just assume. We spend a lot of our time putting our hands together and hoping, if you're talking about eyes. What's happening is you're seeing these in little jumps. You're seeing these in little areas of focus. And the amazing trick here is generally the image seems to make sense. Generally the image seems to have a representational, and it's doing space, and it's doing lines, and buildings look that way fine, even though it has all these problems. Next one. Also shines. So all of these balls don't look like magical, weird, wrong images. Yeah, it's probably a CG ball. But they don't reflect the scene. This one, and that one are not reflecting anything in the scene. Doesn't seem to matter. We seem indifferent to things like reflections. When we are incredibly sensitive to human proportions, we're incredibly sensitive to body position. We can tell position of a body in a painting. And someone with a weird-looking arm looks odd to us, and we'll pick it out. But ball not reflecting the rest of the scene, which happens for every shiny object in existence. Doesn't matter. Next. We do this terribly for mirrors. Next one. A mirror facing this way would never show her face. We don't know this. We don't see this in an image. This doesn't break the image. It's not like bad perspective. It's not like, painting a shadow wrong. For some reason, this illusion is like she's looking at herself in a mirror. Fine. Mirrors don't work that way. And we're indifferent to this. Next one. I'm gonna close on a couple of interesting, eerie images. You've all seen fruit in a glass. You've all seen, a lemon in a glass of water or something like that. You've seen something in a curved glass. You know for a fact that it never does that. But you still see the image. It doesn't break the illusion that this is a lemon in a glass of water and that should be all screwed up, that should be all fractured. And that doesn't matter. You read it perfectly. This is a lemon in a curved glass and the glass is full of water. Next image. Because that's what it should look like. Next one. So it's telling that you can measure people. I believe it's a portion of the amygdala, although it could be the lateral geniculate nucleus. I don't remember off the top of my head. But you can pick figures out of this painting. It's not too hard. There's a lady over there. There's a girl bending down. There are a couple of figures in the background. That's not terribly hard. One way before brain scanning that errors in signal processing, I think it was amygdala errors, were actually diagnosed was by showing someone an abstract painting and asking them if they could see the face. And if you couldn't, it usually meant that you weren't doing face signal processing very well anymore. Next one. And so I'm going to leave you with a really interesting example that we've probably all seen of why you don't necessarily need 3D to make sense of an image and where it sometimes breaks down. Go on, do it, do it. Because you can do this yourself at home and prove to yourself that 3D isn't necessary to see an image as 3D. Oh, go web. Oh. Yay. There we go. All right. So that is my lecture. That is my interest in the brain. Those are my ideas on why your eyes are really crazy and why artists were the first neuroscientists. I don't say that just because I'm an artist. And thank you very much for listening. questions?
Yeah.
Who had yes?
Hey, so I wonder if you could elaborate on to what degree this kind of automatized patternicity could be affected by one's own volition.
Oh, that's really interesting. So you know how I was talking about expertise developing? That you can see with expertise that over time that if you see pictures or faces or come to recognize something over time, that it changes the pathways of information processing in the brain.
Right.
What it also does is it makes it much faster to read an image too. That someone, say you're expert at picking up, say your job involves things that on a conveyor belt, and they could be flipped in one of two directions. And a person seeing a jumble of those wouldn't necessarily know to pick them out and flip them, because they're visually scanning, and they're scanning a lot of information about the scene. Over time, your actual recall rate, right, the rate at which you're looking and scanning the scene, like actually seeing, able to do that signal processing will greatly increase. Because it seems that some things are, that volition of looking at that and studying it and studying the scene again and again, will actually change the way you see the scene. And then you're doing this hyper fast version of it where everybody else who is uneducated about it is seeing less important things.
Do you think there's a negative side to that? Is there any drawback to that?
One thing that it can do is we have a habit of being very blind to areas and images that don't align with something that we've experienced before, or you can pass things by people in certain ways. So there's an interesting experiment called the invisible gorilla, and after I tell you about it, it won't work on you. But there's something called the invisible gorilla experiment, where you have a bunch of people, yes, you know, people playing basketball, for everybody who hasn't seen it, people playing basketball, and then you're asked to count the number of passes they make. They make a number of passes, and the interviewer asks you at the end, how many passes did they make? And you're like, 11. The guy is like, very good. Now, did you see the gorilla? And everybody goes, no. Well, 50% of people go, no. And you show them the video again, right dead center. A gorilla comes in and goes, ah, and walks out. And the problem is, if you're not expecting the gorilla, you have this kind of change blindness where if you're not focusing on something, you can also become insensitive to change in the scene. And so, I mean, everyone who's ever driven for a long period of time has probably not seen a motorcycle. Yeah. Change blind. It's that you will over time start seeing motorcycles. That if you live in a town with a lot of motorcycles or bicycles, the rates of motorcycle and bicycle deaths are actually lower than they are in places that don't have as many bicycles. And the estimate for this is that once you've seen something enough, you start becoming sensitive to kind of its codoil. You kind of sensitive to the gist of it. Yes.
Create images comes from a mindset that is encoded with survival or fear or something where it's grabbing at images.
Oh yeah. Oh yeah.
But there's another capacity of vision actually that comes from a quiet place that actually receives images in a very different way and is actually connecting with the environment.
Oh, you do both. So they're empathetic and fearful. So one interesting experiment is you take all the details out of an image. So you take all the points of contrast, turn it into a line drawing using a computer algorithm. So you can very sensitively change how the line drawing is drawn. And then you blur the image. So you have one line drawing and you have one blurry image. And say if it's a fearful face. So you could show someone a regular picture of the fearful face. And they light up in a certain way. You respond to that in a pretty particular way. You show them the drawing of the fearful face. They have a portion of that reaction. You show them the blurry image of the fearful face, and somehow you react a little bit stronger to that one. The reaction to the blurry, fearful face evokes a greater reaction from you. It spurs a larger reaction. For some reason, the kind of processing that's going on that's not detail-oriented also has a more direct line to the amygdala areas that light up when you have that. I'm looking at someone who's afraid, I'm going to do this mirror neuron response where I'm going to exhibit some of the aspects of fear. You're not going to be afraid yourself, but you're going to start tensing your body for it. You're going to start having this mirror neuron activity that is like a fearful face. You'll have this sort of premuscular movement to turn your face to look like their face. You'll start copying their gestures and micro-expressions and that kind of stuff. But on the other side of that, you also do these things where you can empathize with people in using the exact same reactions. That you can immediately pick apart a face and know a face in a friendly human from a great distance, including things like family members, that you can distinguish them based on very, very small amounts of features. And one of the cool things about that is that we are able to take an expression like a face, like a picture of a face, and then bring back all of this other information from it, like memories and like sense memory, and you can actually like look at a picture of someone from a dozen years ago and you haven't seen them in a while, and you're like, oh, John! And you also get all the memories that are connected with them because you had an immediate emotional reaction to their face.
All right, thank you.